Hi everyone. Uh, After a pretty interesting session, I think what I'll try to do is make it short and sweet and try to give some insights in terms of what we do at Log9 when we are building battery packs for the Indian use case. Uh, I think one thing we have set very clear is the transition to a zero carbon emissions. That has been that's the target that we have set it for 2070. But as we go along, there will be more and more EVs that will come into the in the ecosystem, and when the EVs will come in, there'll definitely be more charging infrastructure will come in to back that EV ecosystem, and more renewable energy that will also come in, that where you will be storing that energy through batteries or other energy storage devices. As far as India's targets are concerned, they are pretty ambitious targets, but given the backing of the government and how things are shaping up in the industry, I'm pretty sure we'll be able to achieve that. But particularly for the Indian EV market, there is a big opportunity, but it also poses some unique challenges. One of the challenges that there's a domination of small vehicle platform. We have more two-wheelers, three-wheelers running on our roads rather than personal four-wheelers. That generally happens in the Western countries, in Europe and the US. The second challenge is the harsh tropical environments. You have high temperature, high humidity that's prevalent across all India. That happens across the year. And batteries are not meant to be used in such harsh conditions. And the third one is the driving pattern and infra, where although when you go to the Western countries, there'll be more sort of gung-ho approach in terms of increasing the driving range. But here in India, because the towns are not that far away, and this is a similar case with China also, the driving range is pretty moderate, but what you want is to juice up your battery in a faster manner, be it with faster charging or battery swapping, which is pretty much required for the Indian EV ecosystem. So, addressing the elephant in the room, there has been a lot of cases of fires, last summer, and we know all the causes of that was, the batteries were not designed in the right way. The quality of the battery packs was also not good. The choice of chemistry was again not chosen in a right way, given what sort of operating conditions we work in. And what it has done is put a dent on the safety and performance reliability of the electric vehicles, and put customers are actually afraid to invest into EVs because of all the performance and safety issues. The other thing is the battery degradation. To start with, your two-wheelers, three-wheelers give you 120 kilometers of range. We have seen that in the industry that, that 100 kilometers of range comes down to about 60 kilometers in a matter of 6 months. And when these kind of experiences start to set in the industry, it sends a wrong message. And the third thing is the self-disbalancing in the battery packs that is pretty much prevalent, but it also addresses much of the wider problem, which is again on the reliability, where your battery packs are cut off either during charging or discharging because they have not been prepared in a right way. What are the preventive and precautionary measures? Although we work on two-wheelers and three-wheelers, there are challenges of putting up a plate cooling-based system or immersion cooling, and you have all these technologies that are available to ensure that either the temperature of the battery remains in a certain operating temperature, certain temperature range, which is suitable for the batteries to work properly. And then, there are safety precautions where you basically contain the fires. There are regulations that came in China last year where you have to give at least 10 minutes of time for the user when the batteries are undergoing a thermal runaway. And there are a lot of technologies that are coming in where you coat the battery packs from inside with a special material that actually forms up when the fire happens, which helps in taking up or contain the fire in that limited region, so that there are no fatalities that happen when a thermal runaway event happens. So what it comes down to, choosing right chemistry. I think the whole, when there were a lot of fires going around across India, be it Chennai or Hyderabad, I think a lot of blame was put on the right chemistry that was chosen. It is now known fact that NMC chemistries, which are high energy density cells, they are not good as far as the thermal runaway conditions are concerned. Because they can store a lot of energy, they also have little tolerance in terms of operating in those harsh conditions. And once the thermal runaway starts, the temperature can easily go to around 900 degrees Celsius, and and the batteries can easily catch fire. So choosing the right chemistry is very important. Again, the other challenge is that because of the smaller vehicle platform, which is two-wheeler and three-wheeler, it is very difficult to put on a right thermal management system without incurring too much cost on the system. So choosing chemistries like LTO or LFP that are meant to be used at a slightly elevated temperatures will help in making better batteries for the Indian use case. The other thing is the right form factor. The industry, be it the cell manufacturers or the pack manufacturers, they are wondering about what sort of form factor that will work in India. The usual suspects are cylindrical form factor and prismatic form factor. Now, the thing is that cylindrical form factor, because of its, it's an ideal pressure vessel where any sort of parasitic reaction that may be happening inside the cell can accommodate those gas pressures within the cell frame, which is typically not the case for prismatic cells. That's why anybody who was using prismatic cells, we have seen the cases where those prismatic cells have bulged up, and there's a distortion in the shape and size of the cell. And when these kind of things starts to happen, they compromise on the safety of the battery pack, as well as on the performance degradation is much faster. Safe and robust wire harnessing. Again, when all those incidents were happening, a major blame was put on the cell chemistry because it was easier to do so. But there are a lot of fire incidents that have happened because of the poor wire harnessing and the absence of any fuses that goes with the battery packs. And if those precautionary measures are taken beforehand, all these high temperature flow and any sort of short circuit that can happen within the EV can be circumvented. Minimize parallel connections. Again, when you have many cells connected in parallel, there's an issue because the BMS cannot sense if any cell has gone through has an overvoltage, which can lead to the bursting of the cell. Now, because for a BMS, whenever you have multiple cells connected in parallel, it takes an average value of those voltages and give that voltage value to the PLC that you have in the EV. Having more parallel connections means that you'll have more and more cases where if there is a certain overvoltage of the cell, because the average out value is lesser than what is being set in the system, you won't know if the overvoltage or there's a shoot up of the voltage that has happened in the battery pack. So minimizing the parallel connections is very much important. And this was also proven in one of the RCA report of the Indian government when the committee came out with a report that because of the parallel connections, the issues, these fire incident issues basically increased because BMS was not able to figure out whether the overvoltage conditions has happened or not. The other problem is the high price of the upfront cost of the EVs. We heard from the previous session that the upfront cost of the EVs is very high as compared to IC, and that has become a major deterrent for the mass EV adoption for India. Now, the thing is that because 50% or almost 40 to 50% of the cost of EVs is because of the battery packs that goes into the vehicle, and in order to decrease the cost of the vehicle, you have to ensure and work on a system where you decrease the size of the battery packs. How you can do it? First is the product standardization. I think that is very important parameter because right now you see cases where 4 kilowatt hour packs are actually going into the two-wheelers. And what it does is right now, because of the FAME subsidies, those those high kilowatt hour packs being to a certain extent being offset by all the subsidies that are being given through FAME 2. But once those subsidies will dry out, the onus will come down to the customer, where they have to purchase a 4 kilowatt hour pack. And as we saw, because 50% of the price of a EV is coming from the battery pack itself, that's going to be a big challenge. So standardization of the battery packs that goes into different platforms is very, very important. And the other thing is that when you are setting up the subsidy distribution, it has to be done in a staggered form. What I mean by this is the first kilowatt hour of the battery pack should be given more subsidy than the subsequent kilowatt hour that are being added up into the battery pack. So that first 2 kilowatt hour, if that gives an incentive to the OEM to keep their packs smaller. And you'll see a trend, and this is already happening in China, where there was increment in the capacity of the packs in the past, but now they are decreasing it down because of the high commodity pricing that are prevalent in the market right now. Cell technology immune to commodity pricing. Again, it also has a correlation between the chemistry that you choose. You have nickel, cobalt, aluminium, copper that's being going into the battery packs. What it will do is the battery itself will become a commodity for the consumer, and it will have a residual value at the end of its life. The problem that right now we are having, in the supply chain is the high commodity pricing. We saw nickel prices going over the roof a couple of months ago. We saw cobalt prices are also increasing. Lithium prices are also increasing. So now we have to make a decision where we choose the right chemistry which are immune to those commodity prices. If I take a case of LFP and NMC for that matter, because LFP has a low commodities, lower amount of commodities that goes into the cell as compared to NMC, they are always going to be cheaper. But most importantly, there won't be a fluctuations in the pricing that would happen as it is happening with the with the NMC battery packs, where nickel and cobalt prices fluctuations will have a direct impact on how much consumer is paying to the OEM. The other thing is the incentivizing of the domestic manufacturing. Although we are, as an industry, we are going at a rapid pace and trying to build up a sturdy ecosystem, but fact of the matter is that even now we have a lot of parts that goes into EVs that are being bought from China and or imported from China and assembled, get assembled here. Incentivizing domestic manufacturing, where you have a certain level of indigenization coming from India, will have a sort of a bad taste maybe in the initial stages, but in a longer run, it's going to pay its dividends, because it's just not about the cells, it's about the motor, it's about powertrain that goes into the EVs. And right now, because of the because we started a bit later as compared to what happened in Europe or the US, the cell manufacturing will take time, because these are the time-consuming industries to be set up. But the production of powertrains, production of electric motors is something that can be done very easily, and incentivizing the domestic manufacturing will have its dividends later in the future. Now, the other point that that's a big debate in the industry is the which technology will win at the end of the day, be it battery swapping or battery fast charging. Although they both have pros and cons, but there are some issues with battery swapping that can be solved with battery fast charging. Now, the one thing is very certain is that in the metro cities, be it Bangalore, Delhi, Mumbai, you won't have scenarios where the charging of the battery packs can be done at home. And we have seen incidents where because the charging was done at home and it wasn't done in a right way, there was a fire hazards that started happening because of that. And in order to ensure that there are safe manners in which a battery can be charged or a vehicle can be charged, and also a lack of infrastructure where you have your own garage where you can charge your vehicles, in all the metro cities, you'll be either dependent on battery swapping or battery fast charging if you want to own an electric vehicle. Now, why we think that the battery fast charging is a better option is because when it comes to battery swapping, you always have a higher inventory of batteries that you need to keep to cater certain amount of electric vehicles that are running in the market. Now, even to support 100 EVs, you need 100 battery packs. Now, if battery swapping comes in, you probably will need 60% more battery packs that will go into that you need to keep as an inventory to run the whole ecosystem. That poses a problem because batteries itself are very costly, and who will bear the cost of setting up those inventories or having a 60% more battery packs that you will need to support that ecosystem. And we can talk about subsidies but they are going to end at the end of the day, and the burden will come on the customer. However, on the battery fast charging, you don't need additional inventory. And these problems can be resolved. The other issue with the battery swapping is the risk of compromising on the EV safety, because you have these batteries that are being taken out and put in almost on daily basis. The connectors of the battery packs, they tend to rust down or they lose their sturdiness, and that increases the chance of any kind of short circuiting that can happen in the battery packs. And that one instance is enough for batteries to catch fire. So there are safety hazards that are that may be prevalent in the battery swapping, but in battery fast charging, because you have these DC chargers being put in, and they are CAN enabled, so they always do their testing in terms of whether the EVs are set to the ground and all the connections are put in a right way, and only then the fast charging will start. So what it will do is it will reduce the chances of any safety hazards that may happen during battery charging or refueling. The other thing is the restriction to a particular form factor. Two-wheelers, three-wheelers batteries are relatively smaller in size, so it's easy to swap those batteries. But when it comes to the trucks and with GVWs of about 7 ton or 8 ton, there will be a huge challenge to set up the infrastructure where you can do the battery swapping of the whole truck, and that's not going to be an easy thing to do. But because fast charging can be done, it's pretty much dependent upon what sort of chemistry you use, what sort of charging platform you use. These issues won't come in the fast charging in battery fast charging application. The final limitation is on the limited product evolution, because the batteries will be designed in a certain way that can complement on the vehicle that will go into the market. So but as a designer, you are pretty much constrained in terms of those vehicles that are going to the market, and design your battery packs according to that. Coming from an R&D side, that's a big sort of a problem when it comes to the evolution of the product, where you can improve the product in an unrestricted fashion. But in terms of battery fast charging, you need to work on different chemistries. You need to work on different form factor that can enable faster C rate at which you can charge your battery. So a product evolution is something that's more that goes with the battery fast charging than the battery swapping. Thank you so much for your attention. I can take a few questions if we have time.
Hi, am I audible?
Yeah.
Yeah. Okay, so my question is about the commodity prices that you mentioned on one of the slides. So, in a cell cost, the nickel or the cobalt would be a smaller component versus if you, let's say, use titanium. So overall, the trend for lithium power backed cells is that the long-term cost of these cells will reduce, and therefore the cost of the battery packs in the electric vehicles will reduce. Of course, it's a different thing that it poses a resale value problem for lenders, but that's a happy problem to have as long as the long-term trend of cost reduction is there. But doesn't using titanium as a part of your chemistry defeats the logic of reducing costs, because it'll continue to remain as a high component of the cell cost.
Yeah. So I think the whole problem is slightly more complicated what I showed in the presentation, because there are different chemistries that are there, but it all depends on how the battery recycling will work out. That will determine what sort of upfront cost that the consumer will pay to the OEM. Now, right now, because the battery recycling in India, it will be very expensive. So moving to a high nickel content or high cobalt content cases will have will not offset the recycling of those materials when that at the end of use of the battery packs. So it all depends upon how faster we will reach to that recycling and doing it in a right way, and the economies of scale will also come into the picture. The evolution which I see is that you'll have battery packs which has less commodity going in. Again, you have to it depends on what sort of final application you're talking about. If it is a fast charging application, then titanium makes a lot of sense, because you can do 4C charging every cycle, right? Which is unheard of in conventional lithium-ion chemistries. But in the initial stages, you'll have less commodity-intensive cells that will be used, especially for B2C case, where you'll be using LFPs more than NMC. But when the recycling will come into picture, and you'll have the residual value of the batteries will have a substantial cost associated with it, then NMC or high nickel content will take a prevalent position when it comes to the adoption of those chemistries in the vehicles.
My question, I mean, it's quite interesting to know about battery swapping and fast charging.
Yeah.
I have two questions.
Yeah.
One, with respect to fast charging, the predominant problem of cell degradation.
Yeah.
So when we go for fast charging or ultra fast charging, say for
Yeah.
example, above 150 kilowatt,
Yeah.
primarily that we see as a very minuscule usage of in a EV ecosystem.
Mm-hmm.
So predominantly it's going to be like kind of less than 50 kilowatt charging, and the fast charging is going to be very small. How do you see that as kind of the cell degradation with respect to the fast charging or charger based system? So that is my first question. Yeah, please go ahead. Yeah.
So again, it's pretty much dependent on the chemistry you use. We at Log9 have been very open that LTOs make a lot of sense for B2B application, because all these aggregators we talked, Mr. Mishra talking about, all these vehicles that you're using, you need to have as less downtime as possible, because these are your revenue generation sources, right? So you need to have a flexibility where you can charge those vehicles in a very short amount of time, 20 to 30 minute operation, and you're good to go. So B2B, we are very sure that fast charging will help, and that's where the difference between power cell and the energy cell will come in. Power cell is more of a give you a scenario where you may have a moderate range, but you can charge them as fast as possible in a very short span of time, right? And the degradation of those cells will also be lesser. It can run up for about 15,000 cycles without much appreciable degradation, as compared to the energy-dense cells, which have a cycle life of about 1,000 cycles. So for heavy duty vehicles where you have more cycles that need to be put in for the day-to-day operation, LTOs make a lot of sense, and because they are the power cells, the degradation of the batteries is very less. Even at high temperatures, even at faster cycling, they don't degrade. They don't degrade at the same level as conventional lithium-ion batteries. I can give you an example. So we have been running tests where we are testing our cells at 55 degrees Celsius, and we are doing cycling at 2C, 3C. And still after 2,000 cycles or 3,000 cycles, the drop is only 3%, or even less than that. So it matters a lot what sort of chemistry you use.
That's quite an interesting subject with respect to the fast charging is concerned compared to the cell degradation.
Yeah.
Again, my second question is towards the battery swapping. So where it is predominantly in terms of battery swapping coming together with smart grids, bidirectional charging, and so where, if you see the European market or the US market, so predominantly the bidirectional charging is coming to a big scenario per se, because you have a lot of cells which themselves are becoming kind of a buffer for the grid itself.
Yeah.
So where you store a lot of energy and you use it for other purpose in terms of even load balancing, things like that.
Yeah.
So how do you see this scenario for battery swapping coming integrated with the smart grids?
So it's a utopian scenario, where you have these batteries also being supported by the grid and vice versa, right? But it's more difficult than it sounds. Taking a case of UK, where they prevented recently any more homes because there was too much pressure on the infrastructure of the power grid. The problem of the power grid is not to generate power, but to maintain that power in a certain frequency when the demand and the supply, or balance that demand and supply curve, right? So this will happen, but this is I would say, 15 years down the line, where the vehicle, the batteries that goes into the cars, which are not used for more than 10% of their capacity in day-to-day life, to actually support the grid, and they are always, they're always being connected to the grid, especially during the night where you have more fluctuations in terms of the power usage of the consumers. But again, you have to see a scenario where you have to cool down those batteries, when it comes to battery swapping, because a huge amount of the big issue is also when you make an infrastructure, you have to set up conditions which are suitable for the storage of the batteries itself, right? And that in itself bears a lot of cost to set those infrastructures and to continue to use those air-conditioned rooms and battery swapping stations. So, again, I mean, it's more of a utopian scenario where it makes a lot of sense, but how the grid will behave to it and will there be a fluctuations that might be coming in because of that, it's still, there are more questions on this than the answers at this point of time.
Thanks for that. I think this scenario is quite prevalent in Europe. I think last even 15 years back itself, they were talking about vanadium liquid batteries storing energy, balancing the grid. And I think for India, smart grids are something like it, as you said, like might be taking 15 years or 10 years.
Yeah. So even in European markets, the size of those battery packs will be smaller. To do it on a grand scale where the whole grid of, say, our northern power grid is totally supported by batteries, that's a whole different scenario, and more complicated also.
Thank you. Thank you.